Okay. All right, good morning, everyone. As usual, questions. Did you guys have any questions from the homework? Please put them on chat if you have any questions. Okay. All right, so let me summarize in a few words what we did. We learned how to compute the determinant for any size matrix, 2, 3, 4, etc. And we established the following important fact about the determinant. And the important fact we established was, so let's call B a n by n matrix. So we've established the following. The matrix B, whatever A, B, whatever you want to call it, is invertible in terms of determinant if and only if, so it's invertible if and only if its determinant is different from 0. Okay, so that's the important fact that we established from the determinant. Besides computing it and studying all its property, we established the following fact. And the way we established it was basically by starting from a matrix, going to its echelon form, and realizing the relationship between the determinant and its echelon form. And we decided that we show that the determinant of a matrix is plus or minus the determinant of its echelon form, as long as there is no scaling going on from here to here. I'm going to rephrase a little bit more again this statement about invertibility. So B invertible, and if B is invertible, it means the determinant is different from 0. And one more statement about that. What can we say about the system Bx equal to 0? So if a matrix is invertible, or if the determinant is not 0, what can we say about the system Bx equal to 0? Quickly on chat. Whatever, just talk. It has a unique solution. It is important. That's why I am really going over it. Unique solution, namely x equal to 0. And we also saw that the columns of the columns of B linearly independent. Okay, so, but remember, this is really the column of B represent, let's say 3 vectors in R3, 4 vectors in R4, and so on and so forth. It doesn't tell me anything about if you have 3 vectors in R4. So it's really very restricted to n by n matrices. So the last piece of rewriting this, but I'm going to do the negation of all this. So the negation of all that become the following. Suppose the system Bx equal to 0 has infinitely many solutions. Infinitely many solutions. So you have a matrix, you solve the system, and you have infinitely many solutions. What can we say about the determinant of this matrix? So you solve a system, and the system has infinitely many solutions. What can we say about the determinant of this matrix? I want answers on Blackboard. I meant on chat. So you have a system. It's n by n. You solve it. You have infinitely many solutions. What can we say about the determinant of this matrix? I would like an answer, please. The determinant equal to 0. Is Jonathan correct? 100% correct. Okay, so if the system has infinitely many solutions, and this is basically the negation of every possibility here. If determinant non-zero, it means the matrix is not invertible. Not invertible causes a pivot. It's not invertible. It means one of the column doesn't have a pivot, will cause this system, when we solve it, to have a free variable and has infinitely many solutions. So if you're solving a system, the system has infinitely many solutions. In terms of determinant, it means its determinant is equal to 0. So, and this is the aspect of determinant that we will use in this class. Even though we learned a lot more about it, or its property, but that's this aspect that we are going to use. Okay, so today we're going to start, we will start the basically chapter 5, the eigenvalues and eigenvectors. What is the eigenvalues and eigenvector story about? The idea is the following. If you have a matrix A, so if you have a matrix A, so I will take the following matrix. The one I have on my notes. Okay. The following matrix. This matrix, you take a matrix and you let it act on a vector. So you multiply it by a vector. And it will definitely give you another vector. So it takes a vector, so that's a matrix A. You can start it with a vector. Let me start with 2, 1, for example. So this is my vector 2, 1. And A will take the vector 2, 1 to somewhere. And in this case, A will take the vector 2, 1 to the following vector. I'm just going to multiply and say where it takes it to. So it takes it to the vector 6 minus 2, 6 minus 2, and 2. Okay? Very interesting vector. Where does A take this particular vector 2, 1? To 4, 2. Now, there is a relationship between 2, 1 and 4, 2. So the relationship is that 4, 2 is nothing more than twice the vector 2, 1. So it acts on the vector 2, 1. And what it does to this particular vector is actually nothing more than stretching it by a factor of 2. So the way the matrix A, so this is A times V, and this is the vector V. So the way A acts on the vector V is by scaling it. It doesn't do that for every vector. So let me say, let me take another vector. I don't know, I'm going to take 3, 1. And see what it does to it. So I multiply it by the vector 3, 1, and I will get the following. 9 minus 2, so now that's a 7, and that's the vector 3. So if I take the vector 3, 1, another vector, 3, 1, at the matrix A, so 3, 1 is somewhere here, for example. 3, 3, 1, somewhere here, that's the other vector. What A does to it, it takes it somewhere else, to 7, 3. So it does not really stretch it by a scalar. So those particular vectors that a matrix, when it acts on them, it means when you take the matrix and you multiply it by them, the effect is only to stretch the vector by a scalar, are called eigenvectors. So eigenvectors are very specific. You start with a matrix A. Eigenvectors are very specific vectors for the matrix that has the following property. When the matrix A acts on them, when you take the matrix times the vector, the effect on it is to multiply the vector by a scalar. So we're going to call 2, 1 an eigenvector, and 3, 1 is not an eigenvector because when A acts on it, it does not stretch it by a scalar. It just takes it somewhere else. So our first definition of today is the following. Let A be a n by n matrix. An eigenvector of A, and that's important, is a non-zero vector x, such that when A acts on x, means A times x, is lambda times x. It means what A does is basically to scale the vector for some scalar lambda. Lambda, it means the scalar that AX will stretch x by is given a name as called eigenvalues. So eigenvectors are, the definition is actually kind of really weird at the beginning, but it's one of the most used concept in very much used concept everywhere. It's actually used everywhere. So this is a simple example. Let A be the following matrix. That's the one I just did. Let V be the vector 2, 1, W to be 2, 0. Is V an eigenvector? It means I'm asking Q, does A stretch the vector V? We just have to compute the vector A times V, and I get 2, 1. Again, I ask the following question. I take a vector W to be 2, 0. Is it an eigenvector? I multiply it by A. So I multiply it by 2, 0. I get 6 times 2. And 6 times 2 cannot be written as a scalar times 2, 0. There is no way you can go from here to here by a scalar. It means W is not an eigenvector. So eigenvectors are vectors such that when A acts on them, it's just scales them, it's just stretches them. So it acts on them in a very, very symptomatic, very simplistic way. So before we start studying, the whole theory and how to find them, let me ask you a question, just to a more geometrical question. Suppose A is the following matrix. Let's say A is the matrix that takes a vector, for example, takes a vector, and it rotates it by 90 degrees. Okay, so that's really what the matrix does. It rotated by 90 degrees. So let us figure out the matrix that does this. So this is my A, it rotated. So it's here. So that's the rotation matrix. So let us figure out, try to remember what's the matrix that does this. To find the standard matrix, that's a rotation. So it's cosine of 90. It's a 0. Sine of 90, that's a 1, minus 1, and 0. That's the matrix. Oh, sorry, that's not the example I want. I want something easier than that. My apology. My apology. All right. I wanted a simpler example. I want the reflection one. My apology for that. So let me take the following matrix. It takes a vector, x, and reflect across the x1 axis. The rotation is a problem. I'll come back to it. So we know what it does. So the reflection matrix is, okay, E1 stays here, and E2 goes here. Okay, so what X does, it takes a vector, and it reflected up here. That's the action of A. And now intuitively, I'm going to ask you the following question. Who can give me an example of an eigenvector for my matrix A? Who can give me an example of a vector such that when I apply A to it, the effect of A is nothing more than stretching X? So can you think of any vector that the only thing A does to it, it doesn't really change, it doesn't move it, it's just basically stretch it? Can any of you think of an example that does that, of a vector? One, I want one, just to show you the effect. Who can give me one vector that said A times it, and I know what A does, it actually reflects. When A times that, it will give me just stretch the vector. Doesn't really do much more to it. Can anybody think of one vector that this will happen? Think geometrically, because the whole point of this lecture is how to find this stuff algebraically. So for this one, I wanted to think a little bit geometrically. Think of a vector when you reflect it. Any idea? It's not very hard. You should be able to find it. Think what A does. Takes a vector, it reflects it, brings it here. Give me one vector that A actually stretches, doesn't really do much to it, except stretching it. Anyone? Okay. Suppose I take the fact vector 1, 0 itself. What does A do to 1, 0? This is the vector 1, 0. What does A do? It reflects 1, 0 with respect to the x1 axis. But reflecting it is actually nothing is going to change in this scenario. It means if I take the matrix A and at times it was the vector x, geometrically is actually going to give me the vector x. This is really an eigenvector for this matrix. And the eigenvalue is the stretching itself. The eigenvalue is the number 1. So it's not a trivial problem, even though with a simple matrix like that, finding those eigenvectors is not really a trivial problem at the, when we see it. However, the goal today is actually to start learning how really we find those particular vectors that the matrix just stretch. So let me go back to my notes. So determining if a given vector is an eigenvector is easy. You just check. The question is how to find those vectors. And the problem of finding them is called the eigenvalue eigenvector problem. So the problem of finding those vectors, specific vectors, we call it the eigenvalue eigenvalue problem. And to be able to solve this problem, I'm going to go back and define eigenvalues again. Because what it turns out to be able to find the eigenvectors, first I need to find the eigenvalues. It means I need to find the scalar lambda. So we start with the definition and then we start working toward it. So what's an eigenvalue? Let A be a matrix. A scalar is called an eigenvalue if AX, the equation AX equal lambda X has a non-zero solution. So I take a number lambda. It is an eigenvalue if I can find a vector X, not 0, such that the action of A on it is lambda times X. This non-zero vector that I can find from here will be called the eigenvector corresponding to lambda. So to find the vector X, turns out to be first we have to find the scalar lambda such that AX equal lambda X has a non-zero. Once we do that, we can pick up our eigenvectors. So that's the way we're going to actually find the eigenvalues and the eigenvector. So I start with a first example. Now all the notes are in front of you, but I will work them out because it's very important to work out this example. So my first example is the following. So lambda eigenvalue, I will write the definition in front of me. Lambda eigenvalue for a matrix A. There is eigenvectors, which is a vector, eigenvalue is a scalar. If when I try to solve this equation has a non-zero solution. Means I can find non-zero X such that this one. Okay, now let us start working a little bit to make it more realistic. So I will take the following matrix, 1, 5, 6, 2. And the question is the following. Show that lambda equal to 7 is an eigenvalue. What does this mean? We'll follow the definition verbatim. It's an eigenvalue means, it means we have to show that the following, that AX equal 7, because that's my lambda, has a non-zero solution. Okay, so what we have to show is that if I try to solve this system, AX equals 7X, I can find a non-zero X that satisfies this equation. All right, now, so far, we've solved a lot of systems, but we've never solved a system where I have a variable to the left and a variable to the right. So here, my X is to the left and to the right. We actually never solved such kind of system. But if, let us remember, basic, whatever, something very simple. If I'm solving the equation, even though that's very stupid, 5x equal to 2x, just, basic. how do we usually solve that? To solve this, if I'm doing it, I put 5x minus 2x equal to 0, 3x equal to 0, and then I divide by x in the scenario. We're going to imitate this idea because I'm solving for x. So this is a 7, that's x1, x2, x1, x2. To solve it, I'm going to put all the unknown from one side. So we'll have to rewrite this as ax minus 7x equal to 0. That's the way I will rewrite it. I go back to this problem. If I'm solving 5x equal to x, it means 5x minus 2x equal to 0. Now, to be able to solve this, I know that this is 3x, but where is the 3 coming from? We basically factored out the x, giving me 5 minus 2x equal to 0, and then I proceeded. So to make the problem easy. Now I would like to do the same. I would like to factor out the x. How can I factor out the x? I'll ask you a question. You tell me if what I did is true or false. Can I factor that this way? True or false?
True.
True? Do you agree with your classmate? Can I factor x this way? Okay, I'm getting a lot of yeses. Okay. Something on this line doesn't make sense. I want you to stare at it one more time. What doesn't make sense? What doesn't make sense?
A minus 7 because it's a matrix subtracting from a...
100% correct. It's absolutely correct. What I write here, it doesn't make sense because A is a matrix, 7 is a scalar. Absolutely nonsense. So I cannot factor out the x because it brings up something that doesn't make any sense whatsoever. So F7 is a scalar, and we know the subtraction, when we talked about how to subtract matrices, you subtract matrices when they have the same number of rows and the same number of columns. So going from here to here failed. So I'm going to erase this line because it's actually not true. And I have to manipulate this expression so things would work. So how are we going to manipulate this expression? We will manipulate it in the following way. I need to bring a matrix somewhere into the picture because I need to factor out the x. 7, I will not touch it. The x, I will rewrite it in the following way. I will rewrite it as the identity matrix times x. Now I'll get back to you. Is this correct? If you take the identity times x, you get exactly x. So going from here to here now is absolutely a correct statement. The identity, which is the matrix 1, 0, 0, 1, multiply it by anything, as long as sizes matches, is give me the vector x back. So I'm not really changing anything. The reason I'm bringing this up, so I can factor my x and I still working mathematically correct. At this stage of the game, I can factor out the vector x because the algebra of matrices tells me you can do that. But now I don't have any more. But now the math makes sense because that's a matrix minus 7 times the identity, that's a matrix. So now I'm subtracting matrices, therefore I am right. So let us see what we are doing. And that's going to be, the heart of what we will be doing today. So show lambda equals 7 is an eigenvalue, means we have to show that this equation has a non-zero solution. So we have to solve this equation. So as I said that we've never solved, so I have to solve it for x. A is a matrix, I know it. 7 is a number, I know it. So solving this, it means I need, basically my problem is, I need to find x1, x2, such that this is equal 7 times x1, x2. That's really the problem I want to show that this equation has a non-zero solution. So to be able to solve it, I mean, that's a 2 by 2, you can solve it easily, but to be able to solve it, I said, I'm going to make it into a homogeneous system. That's really what I am doing. And now I'm going to collect, I want to put the x1 and x2 together to be able to solve it. Now, if it's a 2 by 2, you can tell me, okay, take x1 minus 6x2 minus 7x1. I mean, I know we can do that, but we're doing it in the general context. So I said, okay, I want to factor out this x1, x2. That's the way I want to solve it. To factor out this x1, x2, I cannot subtract 7. So I rewrote 7 as 7 times the identity. So this will give me that a minus 7i2 equal to 0. So lambda equal to 7 is equivalent to show that this equation, which is a homogeneous equation, has a non-zero solution. Okay. Now, I need determinant. I want to bring back the determinant. Under what condition on the determinant? Well, this equation has a non-zero solution. That's exactly what I want. So this occurs if a certain determinant has a certain value. Who can fill in the details now in terms of determinant? So I want this homogeneous system to have a non-zero solution. So in terms of determinant, how can we rewrite that? Determinant of what equal what? Let me go back to the first thing I said today. I forgot my paper, whatever. And determinant equal to 0, 100% correct. Determinant of this matrix has to be equal to 0. Okay, because if A minus, so this is my matrix B that I've talked about at the beginning of the course. So if Bx equal to 0 has a non-zero, in terms of determinant, it means the determinant of the whole B itself has to be equal to 0. So let us recap this piece right there. Recap. So lambda equal to 7 is an eigenvalue. The definition is the x equals 7x has a non-zero solution. That's really what it means. It means it's an eigenvalue if I can find a vector, not 0, such that when A times this vector is 7 times. That's really what it is. Then I manipulate it. I turn this system into a homogeneous system, and I had to introduce the identity to write it properly as a homogeneous system. So I rewrote this, solving this system, which is basically the one I have up here, is boiled down to solve the system A minus 7 times I2 times x equal to 0. And then I told you I want to write this in terms of determinant. So that's a homogeneous system, Bx equal to 0. It's a homogeneous system, has a non-zero solution if its determinant is equal to 0. And that's the fact I use. So this will have a non-zero solution if the determinant of A minus 7I2 equal to 0. So now to check whether lambda equal to 7 is a solution, I actually only have to study the determinant of A minus 7I2. And if it's 0, it means it is an eigenvalue. So that's exactly what I'm going to do. So again, I'll go back to A. And my A is 1562. Okay, that's my matrix A. And I want to compute the determinant of A minus, so I have to find, or I have to show that the determinant of A minus 7 times the identity equal to 0, because the question is lambda equals 7 is an eigenvalue. All right, so I need to compute the determinant of that. So first, let us see how we compute A minus 7 times the identity. I will do that very slowly. A minus 7 times the identity. That's equal to, is the matrix A, verbatim. I'm going to take away from it 7 times the identity matrix, which is, this is the identity matrix. And this is equal to, so I have to subtract those. Now, of course, all of you can do that. So I'm going to multiply this. 1, 6, 5, 2. And this will give me the following matrix. 1 minus 7 minus 6. That's a 0. It will not be affected. So the terms of the diagonal don't seem to be affected because I'm taking 0 from them. The terms on the diagonal, I'm actually taking the 7 from them. So 2 minus 7, which is minus 5. Now I compute the determinant of this matrix. So the determinant of A minus this is equal to, so the determinant of minus 6, 5, 6 minus 5 is equal to, so that's a simple determinant, a 2 by 2. So it's minus 6 times minus 5, which is a 30. Minus 6 times 5, 30. That's equal to 0. So this is equal to 0. It means lambda equals to 7 is actually an eigenvalue. Which means to us, so now we've showed that it's an eigenvalue, basically was done. But for us it means that the system AX equals 7X has a non-zero solution. That's really what non-zero solution. And the solution of it is what we call the eigenvector. So question B is going to be the following. So question A was show that lambda equal to 7 is an eigenvalue. Now the following question is going to be find the eigenvectors that correspond to lambda equal to 7. It means I'm asking you to find those vector x such that A stretch by a factor of 7. We know they exist because we know AX equals 7X has a non-zero solution. The question is find. So question number B, again, is the same matrix. So that's my matrix here. I will not change it. And the question is, show that find the eigenvectors, find the eigenvectors that correspond to lambda equal to 7. So in other words, it means basically, so what does this mean to you? It means we need to solve AX equal 7X. That's really what we have to do. All right, but I'm not going to repeat what I did a minute ago, but again, solving AX equals 7X is problematic because I have the unknown here and the unknown here. So we're going to say that this is basically equivalent to solve the following homogeneous system. So that's equivalent to solve this system. And this will be much easier for us than the original one because we know how to deal with that. We don't know how to deal, especially when it hits 3 by 3 and 4 by 4 system where we have unknowns in both sides of the inequality. So to solve this, I need to solve this system. And now back. A minus 7i, we actually computed a minute ago because we did. So let's do that. That's right. A minus 7. I'm solving a homogeneous system. That's how we solve it. Equal to 0, 0. A minus 7, I got minus 6 in here. We got a 6, we got a 5, and then we took 7 away from the 2, which give me a minus 5. Be very careful. For this system have to have a non-zero solution. Otherwise, what we did before is nonsense. It means when I'm solving this system, I have to have a free variable. If I solve it, I don't get a free variable, I'm doing something algebraically wrong. Either in this problem, I gave you the eigenvalue, but very soon we will have to find them. Either my eigenvalue is not correct, or my algebra at this stage is not correct. So we have to have a non-zero solution. And in this problem, it's very clear what's really going on. So if I am solving it, and I don't like the 6, I divide the first row by -6, would give me 1 minus 1. I divide the second row by a 5, which gives me that. Now I have to row reduce. There is no way out of this. So I row reduce. -1, 0, 0, 0. We have to have a free variable. This is really because, again, the determinant of this matrix is 0, which means that the system A minus 7 I2 times X have to have a non-zero solution. But those two are basically a rewriting of each other. So those are the same. So we solve now. So as we solve, we get X2 is free. And X1 is X2. And every time we solve this, because I'm actually looking for a vector X, we have to write the solution in parametric vector form, because I'm looking for the vector X such that AX equals 7X. So we have to rewrite this in parametric vector form, but that's a simple case. I can set X2 to be my T and my vector. So this will give me that X1 is T, X2 is T, and the eigenvectors have the form T times the vector 1, 1. So eigenvectors are all vectors, all the x's that has the form X equal T times 1, 1. So there are infinitely many of them because we're solving a homogeneous system. And the homogeneous system, once it has one non-zero solution, it will have an infinitely many solutions. So the eigenvectors, all vectors where T is any number except 0. Why T is different from 0? The definition of an eigenvector is a non-zero vector that satisfies. So eigenvectors are the non-zero vectors such that AX equal to lambda X. So the 0 vector is not considered an eigenvector. So the eigenvectors are everything of the form T times 1, 1, where the vector T is different from 0. So these are, so if I want one eigenvector, 1, 1, 2, 2, 3, 3. So basically we have a lot of them. So that's a typical 1, 1, 1. And how can I check? I ask you to check that your answer is correct in a way. So let's check that 1, 1 is an eigenvector. What would you do? So I got something. I want to make sure that I am kind of correct. So I picked one value of T, 1, and I ask you to show that 1, 1 is an eigenvector. What would you do? What's the property of those vectors? I'm listening. I'm really very quiet. I'm trying to listen. So I want you to be able to connect the dots a little bit. So check that 1, 1 is an eigenvector for A that corresponds to eigenvector for A that corresponds to lambda equal 7. What would you do? So what's an eigenvector? We go back. It's a non-zero vector such that AX equal lambda times X. It means it's a vector such that when I multiply A by it, the effect of A is to stretch it, nothing else. Okay, set T equal to 7 and then factor it out by get lambda equal to 7. I set T equal to 1. So you cannot change my T. Okay, yeah. That's fine. Please give ideas. How can I convince you that what I'm doing is correct? How can I convince you that this is actually an eigenvector that corresponds where the eigenvalue is 7? What's the property of eigenvectors? They are specific vectors that A acts on in a very specific way. It stretches them. So if I want to check that this is an eigenvector, I have to take the matrix A and multiply it by that. And I have to convince you that what A does to it is stretch it. It means it's lambda times 1, 1, 1. And it corresponds to eigenvalue 7. It means that's what I should check. I should check that when I take the matrix A, I multiply it by the vector 1, 1, I get 7 times the vector 1, 1. That's what it was going on. So I will do it exactly. I take the matrix A, and I will multiply it by the vector 1, 1. And the question, is it 7 times 1, 1? Is this what A is doing? Now I write A, it's 1, 5, 6, 2. I multiply them, I get the following. 1 plus 6, 7. 5 plus 2, 7. I factor out the 7, I get 7 times 1, 1. So that's absolutely an eigenvector that corresponds to the eigenvalue lambda equal to 7. So if you find them, how to check? You check what originally we're trying to do. Originally, we're trying to find the vector x such that ax equals 7x. We rewrote it this way to be able to find them. But that's really the original question. Find a vector such that ax equals 7x. Ax stretched by a factor of 7. So this process here is the attempt of finding those non-zero. So the answer I'm asking you is your solution is correct. Are those satisfy this property? I take A, multiply it by the vector 1, 1. I do the multiplication, I get 7 times that. So we are definitely doing it right. So geometrically, it means that if this is my vector 1, 1, A times 1, 1 is right there. So when I take A and I multiply it by 1, 1, is nothing more than 7 times 1, 1. So the effect of A is going to take the vector from here and it's going to move it all the way up. So that's the effect of the matrix A on the vector 1. Okay. Please ask questions because it's new, but it's not actually, the algebra of it is really easy. The application are a lot. I hope to show you, 2 applications by the end of the semester. So now I did 2 problems. The first problems, I asked you to show that its specific vector is an eigenvector. The other problem, I gave you the eigenvalue, and I told you verify that it is an eigenvalue. And we went through the process of really trying to show it. So to show that it is an eigenvalue, all right, we say, okay, we want to solve this system, which boils down to show the term equal to 0. The next question is, how do you find those eigenvalues yourself? It means, here I gave it to you, that you check it. And the question now, the second question is, how do we find those eigenvalues without me telling you, okay, this is an eigenvalue, work with it. So the second part is how to find those eigenvalues. So how to find the eigenvalues. And once I know an eigenvalue, I can find the eigenvector that corresponds to it. So question is how to find those lambdas. Okay, and we already built the structure to do that. So let us connect dot. Lambda, an eigenvalue, means that the system, I can find x not 0, such that ax equal lambda x has a non-zero solution. And now, let me ask you a question before I proceed. Why non-zero solution. Why I have a non-zero? Because if I put 0 here, 0 and 0, is A times 0 is always equal to 0. It means this equation always have the 0 vector as a solution, because I multiply A times 0 equal lambda times 0. So it's nothing really. If there's nothing to it. So 0 is always a solution. So to be an eigenvalue, we have a non-zero solution of this equation. So we need it because the definition itself will make no sense after that. So lambda is an eigenvalue. It means Ax equal lambda x is a non-zero. Now it means that A minus lambda x, and this is n, I don't have to have it 2 by 2, equals 0, has a non-zero solution. So lambda eigenvalue, if this homogeneous system a non-zero solution, it means if the determinant of A minus this is equal to 0. So lambda is an eigenvalue if this determinant is equal to 0. So to find the eigenvalue, we find all the lambdas that cause this determinant to be 0. If I find those lambdas that make this determinant 0, for those particular lambdas, I will be able to find the x's. So what's going to be the algorithm, basically, to find the eigenvalues? So to find the eigenvalues, we're going to set the determinant of A minus lambda I equal to 0 and solve for the scalar lambda. Now, once we find those lambdas, to find the eigenvectors, it means we have to find the non-zero x. Basically, we need to solve for those x's. We have to solve this, which is basically equivalent to solve this system, which is easier system. Okay, so that will be the process. So it's not really a hard process. To find the eigenvalues, I need, that's the reason. That's really what I'm doing. I need to find a non-zero vector such that this is satisfied, which is really boiling down to set the determinant of A minus lambda I equal to 0 and find all those lambda that satisfy this condition. To find the eigenvectors, I just have to solve Ax equal lambda x. It means by rewriting that, it means I have to solve the system A minus lambda I x equal to 0. And now, of course, let us start with examples where we're going to do the whole thing. I will give you a matrix, and we will find the eigenvalues, the eigenvectors, and we will check if our work is correct or not. So here is our first example. Because the algebra can get messy in those problems, and you guys will realize that. So I will take a matrix where the algebra is not too messy. So let A be the following matrix: 1, 3, minus 1, 5. And the question is, find two questions. First, find the eigenvalues. Okay. So it means, how do we find them? Basically, we set the determinant of A minus. This is a 2 by 2 matrix, so that should be equal to 0. And we solve for the scalar lambda. So let's do that. First, we have to compute A minus lambda I times the identity. So we compute this. A minus lambda times the identity. And we'll compute slowly the first time. After that, it will be very clear. Minus lambda times the following. So A is 1, 3, minus 1, 5. And the identity is 1, 0, 0, 1. Let's compute this. So this is equal to what? 1. Okay, I rewrite it because it's the first time. Minus multiplying a matrix by a scalar means that you multiply every entry by a scalar. So let's see what we get here. It's 1 minus lambda. So basically, minus 1 minus 0. So the term of the diagonal, I'm not taking anything away from them. I'm taking 0 from them. They're not really being changed. 3 minus 0, that's 3 has to remain. 5 minus lambda. So when I'm taking a minus lambda, what I really do, I'm taking lambda from the terms on the diagonal, and I'm not really touching the other terms. Now we have to compute the determinant and set it equal to 0. And we will compute the determinant using cofactor expansion. We will not use row reduction for those, because row reduction is very, very hard for those problems. So we actually use cofactor expansion. So in this problem, it's a 2 by 2. There is really nothing to do, nothing about it. So it's going to be 1 minus lambda, 5 minus lambda, minus plus 3. And we have to solve. So when we compute the determinant, as you realize, that's an equation in lambda. It's a quadratic equation in lambda because the highest degree is going to be 2. And the problem really boiling down to solving this quadratic equation. So we will solve this quadratic. So how to solve quadratic? We just, in this problem, the only way out is, so basically, I want to set this equal to 0 and solve for lambda. That's really what I want. But the easiest, the only way to do is we're going to distribute, and then we will solve. So we will distribute lambda, lambda. This will give me a lambda square. And then I will have minus lambda, minus 5 lambda, minus 6 lambda, plus 5, plus 3, plus 8. And basically, I want to solve this equal to 0. So that's a quadratic, we will solve it. Okay, so how do we solve a quadratic? 2 ways, not 3. Either you factor or use the quadratic formula. Of course, I cook the problem so we can factor because I don't want hard numbers to deal with. So that's a 4 and the 6, so the 2 and 4 are really. So that's a lambda, and it's a lambda, it's definitely that. So this is equal to 0. It means I have 2 eigenvalues. Lambda equal 4 and lambda equal to 2. So those are the eigenvalues. Means for each one of them, I should be able to find a vector that x stretch by 4. And for this, I should be able to find a non-zero vector that a stretch by a factor of 2. That's really what I should be able to do. So question number 2 is, find all the eigenvectors that correspond to lambda equal 4. And then find all the eigenvectors that correspond to lambda equal to 2. So we will do that. We will be quite patient. So now I have to keep this in front of me and pick up another paper. All right. So we will do that. So question number B is find all the eigenvectors we should not confuse vectors with value. Eigenvalues are the scalar, eigenvectors are vectors. Find all the eigenvectors that correspond to the first value, lambda equal to 4. And we know we have infinitely many of them because finding them, it means solving a homogeneous system. And the homogeneous system, when we solve it, either the solution is unique or infinite. And in this case, we know we have to have a non-zero solution. It means infinitely many. So we have to solve basically ax equals 4x. We have to solve 4x. but immediately. It means we have to solve this system because this one we problematic. So I have to compute a minus 4 and proceed. So what is a minus 4r? Is the following. Okay, this is my a. I put it back in front of me. I have to take a 4. So I'm going to take the 4 from the diagonal. 1 minus 4 minus 3 minus 1, 3, 5 minus 4, it's a 1. That's 4 minus I2. Be very careful. The determinant of this is 0 because that's where we got the 4 from. When I'm going to solve this homogeneous system, I have to have a free variable. So let us solve it. So I have to solve the homogeneous system. So I write it, minus 3, 3, minus 1, 1, etc., 0, 0. Of course, it's clear that this is my reading. Of course, minus 3 plus 3 is 0, minus 1 plus 1 is 0, and then I will have minus 3, minus 1, and 0. And because I don't like minus 3 here, I multiply by 1, make it 3 and 1. Now we solve that. My solution would be x2 is free. And this will give me 3x1. So this will read 3x1 plus x2 equal to 0, giving me x1 is minus a third x2. So my solution would be x2. The solution has to be always written in parametric vector form. And x1 is minus 1 over 3t. So every eigenvectors, so the eigenvectors will have the form t times minus a third and 1. And t is non-zero because I'm describing the eigenvectors, and 0 is not an eigenvectors. So the eigenvectors are all vectors of the form a scalar times minus third 1. So geometric, so I have infinitely many of them, not 1, not 2. So let us describe those vectors. So they are all the scalar multiple of that. So minus a third will put me right here. 1 will put me right here. So that's basically my first vector. So this is minus a third 1. And every vector on this line, every vector on this line, the same line, is actually an eigenvector because every scalar multiple of this vector is an eigenvector. And we're going to call this line something special, but let us first check that my work is correct. Now I get back to you. How do I check that those are actually eigenvectors? What would I check for? Now back to you. How can I convince you that, I'm doing the right thing? What should those vectors? Go ahead, I'm listening.
Check the original equation, ax is equal to lambda x. Plug in x for it.
So, and what should I should check what? You're right, but I should check what? That if I take a times by this vector, what should I get? What should I get?
A scalar times x.
Which scalar?
Oh, 4.
4. That's what you should get. 4 times x, because those vectors are the solution of this equation. That's the connection I want you to do. Those vectors are the solution of that equation. So to check myself, I want to check that those vectors I'm really looking for are those vectors that A stretched by a factor of 4. That's the factor. That's what I'm looking for. So I will do that. Be very patient and I'll do it. So a typical vector has the following form. A scalar times that. So it's a scalar, so I'm multiplying. This is a matrix, I'm multiplying it by this vector. Equal. Now, one of the property of multiplication is scalars could be taken out. Only scalars can be factored out just to make the math easy for me. That's linearity at work. Scalar could be moved out. This is equal to T times my matrix A. I'm going to multiply it by my vector 1, 3. I'm just checking that my work is correct. Now my matrix A, I have to pick it up, was 1, 3, minus 1, and 5. Okay, so this is equal to T is my scalar that now let's see what I get in here. Minus 1/3, minus 1, minus 4/3, and 3 times minus 1/3, that's a minus 1, and a minus 1 plus 5, that's 4. And of course, I can factor the 4. And if I factor the 4, what would I get? 4t times minus 1/3 and 1. So now, obviously, we should realize what we have. So I took the following. That's my vector x, my original vector, and it's equal to 4 times the same vector, which is t times minus 1/3, and that's my vector x. So I'm absolutely found all those vectors that A will stretch by 4. So geometrically, if this is my vector AX will be going right there. That will be my vector A times minus 1/3 1. It's 4 times minus 1/3 1. And those are particular vectors because A does not stretch every vector. A lot of vectors just move them somewhere, but it just stretch those particular vectors that we call eigenvectors. All right, now we do C. The last question is the eigenvector that correspond. We have two eigenvalues. We have lambda equal 2, lambda equal to 4. So the last one is find the eigenvectors. Find the eigenvectors that correspond to lambda equal to 2. So this is another set of eigenvectors that A will stretch, but it will stretch by a smaller amount, by a smaller scalar. It's going to stretch by 2. So again, to do that, we have to solve, that's the lambda, we have to solve this system and find the non-zero solution. So we solve it. At this stage, 0, 0, A minus 2i, I have to put A in front of me. So this is A, I have to take 2i, it means I have to take 2 from the diagonal. 1 minus 2 is minus 1. The terms on the diagonal are not being affected. This is a 3, and this is 5 minus 2, which is a 3. Okay, again, as we realize, multiply this by 3 and add it. Multiply this by 3 and add it. And this is going to be minus 1, minus 1. I do one more row operation. It's going to give me that. So we solve and we get the eigenvectors have the 4t times 1 here. And this one would read x1 plus x2 equal to 0. x1 is minus x2. And my x2 is 3. Minus 1. And graphically, geometrically, it means these are those vectors. So minus 1 and 1, minus 1 and 1. This is a vector. And that's not the only vectors that A stretch by a factor of 2. A will stretch, if I take anything here on this line, because the eigenvectors are all the vectors that are a scalar times minus 1, 1. Means if I take any vector on this line, any vector, I pick arbitrary vector, then I take it, I times it by A, I will get 2 times this vector. So A will stretch it by a little bit. This will go to here. Now, okay, as if you didn't have enough terminology today, another terminology, which is the following. When I'm finding the eigenvectors that correspond to lambda equal to 2, I found infinitely many of them. A lot of them. So not only one, minus 1, 1, 2 times minus 1, 1, 3 times minus, so we have a lot of them. So we will give them a name because we like names. And we're gonna call them eigen. We're not changing the beginning, but I'm looking at all of them. We're gonna call them eigenspace. So eigenspace is the collection of all the eigenvectors that correspond to specific eigenvalues. So the eigenspace, so for this, we're gonna call this eigenspace that correspond to lambda equal to 2, and we will use the following notation. E for eigenspace, but it's a capital E, and at the bottom here, we write 2, which means that this is all the eigenvectors. So the big E tells me that you're looking now at all of them that correspond to lambda equal to 2. So the 2 is basically the eigenvalue, the value of the eigenvalue. So all of them. So the eigenspace really is all of them. So it means every vector of the 4 minus 1. So let me define eigenspace now in a formal way. So what are the eigenspace? So, sorry, it's on my notes. Let me find eigenspace. So let A be a n by n matrix and lambda an eigenvalue. Then the eigenspace of A corresponding to lambda that we denoted by capital E lambda is defined as follows. The eigenspace is all the eigenvector that correspond to lambda, because for every lambda, so if I have my eigenvalues, it means my system AX equal lambda X has a non-zero solution. It means it has a lot of them. So E lambda is all of them, all the eigenvectors that correspond to lambda, but we will throw in the zero vector, which is not an eigenvector. That's why I said with the zero vector added. So basically, what's E lambda? Basically, E lambda is nothing more than all the solution of the homogeneous system A minus lambda IX equal to 0. So all of them, because the eigenvectors are nothing more than obtained by solving this system. So another way of writing the eigenspace is all the solution of the homogeneous system. Now, solution of homogeneous system, we gave them a name. Of course, it's in my note, you can see it. But what's the name that we gave to the solution of the homogeneous system? Can anybody recall that name? We gave a name to all the solution of a homogeneous system. So if I have a matrix A, not A minus lambda, because this is confusing you a little bit. In general, if I have a matrix A, and I look at all x's such that AX equal to 0, what did we call all those vectors? The null space, absolutely the null. And we found a basis for the null. And that's exactly the same. So now instead of A, I have A minus lambda IX. So E lambda will be the null of A minus lambda. So that's what really E lambda is. So it's basically all the eigenvectors with the zero vector added, but the eigenvectors are obtained by solving this system. So in the previous example, the example I just did, what is E2? E2 is the following. Okay, E2 was, I usually lose my papers. I don't keep track of them. Okay. Let me figure out where I put E2 because I want to. Okay. That was my, sorry guys. I keep finding E4, but I'm not finding E2. Right, so I look at my notes, and what was E2 in my previous example? In my previous example, E2 was all the eigenvectors that correspond to lambda equal to 2, and this was all the scalar multiple of the vector minus 1, 1. So in the previous example, that's what E2 is. Since I didn't find it, I have to rewrite it. So E2 was all vectors of the form T times minus 1, 1. This is all the eigenvectors that correspond to lambda equal to 2. So E2 was the null of that. It means all vectors, which is a scalar times minus 1, 1. Means E2 is nothing more than the span of the vector minus 1, 1. So the basis for E2 is this vector. So E2 is a null, like we've seen the null before, and the basis for it was obtained by writing every vector in a parametric vector form. So the basis would be the vector minus 1, 1. Now for E4, it's the same thing. It's the null of A minus 4i. And those, it means all the eigenvectors that correspond to lambda equal to 4. Means all the solution of A minus lambda I equal to 0. And those are all vectors of the form scalar times minus third and 1. So the basis for E4 is the vector minus a third 1. But here, I put something on your notes. I told you that we can pick this as a basis or minus 1, 3 as a basis. Am I correct? Am I correct? Yes or no? Explain. Can I have two different bases for the same thing? Right, we write it like this because I don't like fractions much. Can I use this vector as a basis instead of that vector? Who say yes, who say no? They are scalar, absolutely. They are scalar multiple. They are absolutely scalar multiple. This vector, take 1 multiplied by 3, you get minus 1 and 3. And you're working with a line. So basically, that's scalar multiple. It doesn't really matter. So this is the vector minus third and 3. Sorry, and 1. This is that vector. So its span, it means every basically scalar multiple. It means every vector which lies on this line. Now, if I take the vector minus a third and so minus minus 1 and 3, it's nothing more than the vector right here. This is the vector. So I just scaled it. So if I take all the scalar multiple of that, again, I will get every vector on the line. So it doesn't matter what you will take for a basis, whether you take that or that. So the dimension of E4, and here I remind you that the dimension is the number of vector in a basis. So the dimension here is 1 because this is spanned by one vector, and the dimension of E2 is also 1 because it's spanned by one. So what is now the eigenvectors, eigenvalue problem, and what does it mean to solve this problem? Solving this problem means, first, we have to find the eigenvalues, and this is obtained by setting the determinant of A minus lambda I equals 0. Second, we have to find the eigenvectors for each one of them. And the way we usually find them is we find a basis for the eigenspace. So we solve the system, and then we say, you know, I don't have to give you all of them. If I give you only the basis for E2, I'm practically giving you all the eigenvectors, because if I give you the basis, I'm telling you that everything else is a scalar multiple of the basis in case you have one vector in the basis, of a linear combination of the basis in case you have two vectors in the basis, which we can have and we will have in my example next week. Okay. All right, so my last example, which is on the lecture note, we don't have time to do it, but I will, of course, I will start with it next time. Okay. Any questions before I let you go? Now I know, guys, yeah, you are wondering about your exam. Definitely, I don't forget that. I'm working on it. It's just taking time because all my classes had exam at the same time. I'm almost 80% done with it, so I hope that you guys will have it by Thursday. I mean, the grade will be on Blackboard with the comments on each one of you. Okay? Any other question before I let you go? All right, stay safe and enjoy the rest of the day. Bye-bye, guys.